Welcome to Catastrophes. This is a podcast about disasters, why disasters happen, and the factors that make them happen. We explore the underlying vulnerabilities of cities, countries, communities, and we also look at the hazards in which cause many of the disasters. And today, I'm joined by Dr. Jeff Kavanaugh, a glaciologist from the University of Alberta, for a discussion about glacier melt and the subsequent secondary hazards and other risks that glacier melt poses. We have a number of discussions ranging from the force or the amount of impact a glacier and a glacier-induced landslide can have, among the GLOFs, which I'll let the interview speak for. And I hope you enjoyed today's episode. I certainly had a great time learning about all this stuff. And with that, the intent of exploring disasters is not to demean or diminish the experiences of people who are facing these traumatic and difficult situations, but rather explore, question, critique, and ask why disasters happen the way they do. And one of the ways we're going to learn today is we're going to ask why these events are happening the way they do, and how climate change is impacting how glaciers melt. And with that, let's begin. Welcome, Dr. Jeff Kavanaugh. You are an associate professor of the Department of Earth and Atmospheric Sciences at the University of Alberta, with a specialization in glaciers and today's topic, glacier melt. So I've been looking forward to this interview for I think a few weeks now, ever since we kind of started to touch base, and I think this is going to be an excellent episode. But I wanted to just quickly touch on a little bit of your background before we get into, the topic of risk and glaciers and all the hazards that they can bring. So your research interests are really interesting, and I might pick your brain a little bit on them, but you're investigating the dynamics of glaciers and ice sheets, the impact on their landscapes, and then also climate change and the overall response of glaciers and climate change. Really fascinating. And just part of your background, I think, which is also interesting, is how you go about doing these things and the testing of it. So you're using a combination of novel situ field instrumentational and numerical modeling techniques. And I've read a few of your papers, but your research has taken you from, Jasper, Banff, Western Alberta to British Columbia, Yukon, Alaska, the high Arctic, which is really interesting, but then also Antarctica. And I'm definitely going to want to hear about that. And the other thing is you have your background in physics from Sonoma State University, and then you have your PhD in geophysics from the University of British Columbia, and you've been a part of University of Alberta since 2005. So going on 20 years now. What a track record. Welcome, and thank you for joining Catastrophes.
Well, thank you very much, Brady. I've been looking forward to this as well. And yeah, I feel pretty fortunate with what I've been able to, where I've been able to go, what I've been able to study. And it's been a really interesting and challenging and rewarding time. So thank you for having me here.
Yeah. I mean, I guess the first question we have to ask is, how do you get into researching glaciers? How do we do that?
It's a really circuitous route that I took. So I was lucky enough to be born to a field biologist, and I'm one of 5 kids, and so as a biologist with 5 kids, the money doesn't go all that far, and so I mean this truly, the blessing of that was that all of our family vacations were my father's research trips. And so my father's interest was in beetles that live near ice fields and mountain streams and glaciers. So all of our vacations were to the mountains of North America. So long road trips, multi-month road trips to visiting all the mountain ranges. And I just fell in love with essentially doing work in the mountains. And some of my earliest memories are those trips and the hikes we took and all the little special places we got to visit. But when I went into university, I graduated high school in '87, and at that time, if you did pretty well in school, you were expected to go into engineering. So I started my career in aerospace engineering at San Jose State University. And after a couple of years, when the foundational courses were coming to an end and the engineering courses were taking off, I realized how much more interesting physics was to me. And so I decided to switch majors, and I then also at that time switched universities from San Jose State to Sonoma State. And Sonoma State had a really tiny physics department right next to a very tiny geology department. And so I took a few geology courses and had enough fun in both of those and got to know the profs in those two departments well enough that it was really more of a mentorship than an undergraduate education. And so my original plan with physics was to go into optics. I'm an optics nerd. I love cameras. I love telescopes, microscopes, anything optical. And I even worked for a year and a half as an intern at an ophthalmic instrumentation company. So in the R&D department, where they make machines that measure characteristics of your eyes. So that was my original plan, maybe even a PhD, MD. But then I realized that would dedicate me to a basement laboratory where the ground isn't shaking and there isn't extraneous light. And I started to think, what physics can I do in the mountains? And what can I do to combine my new interest in geology? I'm not a geologist, mind you, but have a bit of that information. And glaciology fit the bill. It's a place you can do physics. Glaciology is a very broad field, but among those various disciplines is physical-based glaciology. Sorry. So, what controls glacier motion? The strength of the ice, the nature of the contact between the ice and its bed, how that contact changes when water reaches it and is pressurized by the addition of more water. So what worked out for me is that my initial training in some engineering courses, material properties, stress strain, all that, played right into glaciology in addition to the physics and geophysics. So it was one of these unplanned but very serendipitous routes that just worked out well. And really, I don't know that I certainly wouldn't be the glaciologist that I became, whatever that is, without my foundation in engineering and physics. And so it's physics. Physics is grounds how I approach problems. It's why I do numerical modeling. I'm always been a tinkerer, so the instrumentation comes naturally to me. You can't buy off-the-shelf subglacial instruments. You have to build them and calibrate them.
Wow.
So again, a very fun path, not a direct one, but it also helps me when I'm, teaching undergrads. I always let them know that you can create your own unique path through this strange world that we're in, and you'll have a skill set that nobody else has if you do that, rather than following the same path that everyone else does, where you're a carbon copy of the rest. So forge your own path. That's what I'm trying to say.
That's brilliant. And I mean, like, even my own background, like I came to the field of disaster management through an undergraduate degree of political science. And so I always thought about, like, how do institutions, really go about doing this and this, and really the first time I think I ever researched the disaster was desertification in northern Sahara, and how North African countries were approaching their strategies compared to, like, sub-Sahara Africa looking at the Great Green Wall desertification. Anyways, I've always really enjoyed these slowly unfolding disasters, the ones that they're not glamorous, but they're really mundane, I guess I think is the best word to describe them, until something happens. They trigger something. And glaciers is one of them, right?
Yeah, we have those too. We have some fast disasters and some slowly unfolding, seemingly unstoppable disasters coming our way.
Yeah, brilliant. I love to hear about people's background, because it's always interesting. You always see that little bit of the background and how you're approaching the problem and how you're talking about things. So thank you for that. I really appreciate it. So let's start off simple. We're all new to glaciers. We have you, the glacier expert. How do we define a mountain glacier, I guess, just as at its core? What's the base definition?
Yeah, I mean, that's the perfect place to start. So Essentially, they're locations where every year you receive a bit more snow in the wintertime than you lose in summer. And so if you put snow in the landscape, it'll sit there. If it's allowed to persist, it'll change form. It'll start out jagged and clean and shiny, or bright white. It'll age, so the crystals will round off. They'll compact. You'll get a bit of windblown dust, maybe some smoke particulates. Whatever lands on the snow incorporates into that. But if it persists long enough, the next year's snowfall lands on top and weighs it down a little bit. And the following year's snowfall falls on top of that and weighs it down. So you have these processes of change within the snowpack, but also of weighing it down with subsequent new layers. And so if you keep adding new snow on top and you accumulate enough, you compress that snow eventually into ice. And that's a process that can take decades to centuries, depending on where you are. In the Pacific Northwest, where we have snowfalls reaching 100 feet per year in locations, it can happen over decades. In Antarctica, it might take a few centuries in the very center of the continent, because there's so little snowfall. It's so light, and so it just takes that long to compact. But once it starts to accumulate as ice, so once it's thick enough, compresses to ice, and you keep adding volume and thickness, at a certain point, it can become thick enough to start to flow under its own weight, to form. It's a solid, but it's very near its melting point. So it's like a hot metal, and it deforms in a very similar manner, actually, to hot metals. So once it starts to flow under its own weight, that's when we call it a glacier. Wow. Yeah. And so what you tend to have with a glacier as well is, when you go higher in mountains, it gets colder. Most of us have experienced that. You also tend to have more snow depth, more accumulation up high. There's just more snowfall up high than there is lower. And at lower elevations, it's warmer and you have less snowfall occurring. So over the course of a year, the entire glacier might receive snow, but by the end of summer, the lower portion will have lost the new snow and some of the ice beneath it. Whereas up high, you've gained more snow than you've lost, and so that adds to the mass. So you've mass added up high, mass lost down low. And if it weren't for the flow, the glacier would just keep getting steeper and steeper and thicker and thinner. But the flow kind of adjusts for that and replaces, generally speaking, in a healthier climate, the added mass up high flows down to replace that is lost in the summer. So glaciers reach a kind of a steady state, given the climate they're in, where the amount of accumulation overall in this upper area, the accumulation area, is balanced by the amount lost down low, and you have the flow replacing that loss from up high to down low. So it's a dynamic system, kind of a battle between climate, which gives you the snowfall and the melt, versus dynamics. And so the response of glaciers is both climate driven and dynamics driven.
That's really cool. And so like the geography of it, your geography background really comes into play there too. The geography will inform a little bit of the lower. Very cool. This is all new information to me, and likely my viewers too. So you're going to see some aha moments as I'm
right on.
as I'm on camera and exploring that. So one of the questions that just came up for me as you're explaining that, you talk about, process of the snowpack and whatnot. So we've had a lot of prolonged wildfire seasons where there's been a bunch of snow in Western Canada. And so is that smoke, is that like wildfire, the excess from it, is that influencing our glaciers over like today?
Yeah, it is. There's a number of studies now looking at the impact of black carbon, so soot, on glaciers, and that can be industrial, but more and more it's wildfire. I mean, wildfires have been actually occurring for forever. As long as there's been forests on land. So what, 420 million years or so. But they are more intense now. They are. I've had more smoky days on glaciers lately than earlier in my career. I remember one smoky day in Yukon when I was doing my PhD up in Columbia National Park, and now you can have weeks of smoky weather up there, or up in the Rockies. So it's definitely an impact. And smoke on ice, smoke on snow, that particulate matter absorbs more energy, so less is reflected,
Yeah.
and so it accelerates melt. And so yeah,
Wow.
even the smoke component of our current climatic change is having impact on glaciers.
And it's funny you talk about Yukon, because the episode just before this, I interviewed a wildland remote firefighter in Yukon, and
Yeah,
he talked a lot about a lot of forest fires up there are occurring in really remote areas where they're
yeah,
close to the mountains. We can't really get to them, but we know that they're there because a little bit of the smoke. So that's an interesting component, a little bit of a negative feedback loop of glaciers and whatnot.
yeah.
Wow.
Sadly, we call this one a positive feedback loop because it amplifies a change, right?
Oh,
So
okay.
it grows so a positive feedback loop
Yes.
will increase the effect, whereas a negative one will dampen it.
Oh.
So yeah, so this is one of those unfortunately positive feedback loops where warming gives you more fires because the fuel's drier.
Right.
It also decreases the energy reflected off a glacier, so that makes the glacier retreat, exposing more ground, which absorbs more heat. And so it's one of these really concerning feedbacks.
Yeah, no doubt. And part of a large change to our ecosystem too, right?
Yeah.
So one of the lingering questions for me, and as I've been preparing for this episode, I've seen a few terms, and I think we need to talk about a few of the terms just so we're
Good.
all on the same basis going forward. Can you tell me what debuttressing or debuttressing means in that word?
Debuttressing.
Yes.
Yes. So yeah, every field loves their terminology. I like to think of myself as an exception where I can speak those terms to those that need to hear them, but they're a disservice to everyone else. So I'm happy to talk about these things. So imagine glaciers, once a glacier is present on the landscape, so once it's grown thick enough to flow, that flow is of rigid ice. So rigid, yeah, it's a solid. Over long time scales it flows. But because it's a rigid material, it erodes more effectively than water does. And so river waters can remove materials from within their banks. So anything that falls into that river bank is subject to removal if it's small enough for the water to carry away. So faster water flow can carry bigger things. More volume of water can carry more stuff. Glaciers can carry anything. They're rigid. So if a house-sized boulder, if a building-sized boulder falls onto the glacier from a slope above, the glacier will happily carry that building-sized boulder down valley. Because they're rigid, they can scrape away much more of the mountainside than a river can. So a river ends up making a V-shaped valley.
Yeah.
Glaciers end up making those beautiful U-shaped valleys.
Mm-hmm.
They also end up creating these beautiful basins called cirques in the mountains, so that any bowl you see in the mountain any mountain range on Earth was likely carved by a glacier. They scoop out these kind of armchair shaped basins, and then they travel down. If they are extensive enough to leave that cirque basin and flow down a valley, they're called valley glaciers. Then creating that U shape, but also carving out very deep bowls along the way. And so if you've ever hiked the Joffrey Lakes Trail in BC, there's a chain of 3 lakes, and that's the glacier carving a bowl, carving another bowl, carving another bowl. So they do this weird undulating form, and so they leave these depressions that can fill with water. So that's a potential hazard. They can fill with sediment. So glaciers create a lot of hazards by breaking up the landscape, providing water, and so you have this. Now we have this U-shaped valley. To get back to your question, U-shaped valley filled with ice. So imagine my hands here with an ice filling to the rim. There's no way with the ice present for this slope to fail, right? Because the glacier is pushing back against the stresses of the mountain. If you remove the glacier, you've completely changed the stress field there, because there's no longer the glacier pushing, supporting, buttressing that slope.
Wow.
So removal of ice debuttresses. It removes the force acting to maintain pushing on that slope to maintain it.
Right.
And so by removing glaciers, you can trigger massive landslides. There's one future massive landslide being watched as it develops right now in a location called Barry Arm in the Puget Sound region of Alaska.
Yes.
And this is the largest pending landslide I'm aware of. It's pending enough that they are constantly monitoring it. They have various systems monitoring in real time, monitoring its motion in real time. They have radar systems, lidar systems, I should say, and so they can track its motion in real time, and they can send notices out because there's a lot of tourist activity. There's cruise ships that operate in Puget Sound. There's fisheries that operate there. The town of Whittier is about 50 kilometers away. It's kind of a straight shot down the fjord system, and so if let me pull some numbers up here about that. So that slope, I believe the discovery of its impending failure was accidental, but the result of, so what's happened is that this glacier, again, flowed from land through one of these beautiful valleys into tidal waters, into Puget Sound. And so it's sitting in the fjord that it created. And so that the position of the lowest extent, the terminus of the glacier, was pretty stable between 1954 and 2006. And after that, it started to retreat. And since 2006, it's retreated roughly 3 kilometers. So that's about 2 miles. Perfect. And so what
Right
you see
on
here is, so the extent there, you see a black circled area. So the glacier in this image is extending further into Barry Arm. So this is a precursor situation. And then it retreated back to that purple line where it says front 2020 / 0310. So it's retreated those 3 kilometers, right? So there's the 4 kilometer scale bar at the lower left. And that black area is now moving. And for scale, that circled area is about 1 kilometer in height, in vertical height from the water to its top. It is about 2 kilometers long. And it's inferred to be about 174 meters deep.
Oh my God.
So that mass, there's a few different blocks to it that are moving at slightly different rates, but that mass is thought to be something like 455 million cubic meters of rock.
and when that, holy.
And so now the glacier has backed up to essentially debuttress almost all of that mass. And so they're monitoring because it is essentially going to fail. And how it fails will determine what sort of response will occur. Because if it all goes at once and slides into the Barry Arm Fjord, it could create a tsunami wave that might run up as high as 300 meters up the opposite side. So 1,000 feet, vertical feet. And they expect that large waves and very strong currents can run through the entire Puget Sound system, threatening the town of Whittier, like I mentioned, 50 kilometers away, just down the Harriman Fjord, I believe. I believe that's where it is, going off to the kind of southwest.
Going southwest,
Yeah, but also if you're on a cruise ship, if you're on a kayak, and there's 3 meter per second currents resulting from this 100 kilometers away, you probably won't get the notice because you're in a kayak. You probably will wondering what the heck that wave is doing coming at you. So just imagine the hazard here. It's remarkable how much potential there is here. So what's really, the way I view these things is from the point of view of physicists, and that's looking at the energies involved. And so I've worked up a few numbers. So the strongest man on Earth, Hafthor Bjornsson, recently broke the record for deadlift. Okay, so he's the first human to ever lift 510 kilograms. Remarkable. That's a remarkable lift. I cannot fathom that strength.
Yeah, no.
I just can't even believe it. So he lifted about a meter, right? Probably less, but we'll give him a meter off the ground.
Yeah.
And so to do that, to lift 500 kilograms, 1 meter vertically at Earth's surface, which has acceleration of due to gravity of 9.8 meters per second squared, that takes 5,000 joules of energy, which is pretty remarkable.
Yeah.
For a few seconds. It's probably a 5-second lift, so that's 1,000 watts of energy that he is producing for those 5 seconds. So let's put that in context. This is the biggest of the events we're going to talk about. So I thought we might build here, but we're going to go huge right at the beginning. Yeah. And so for scale, let's jump from a human output of 5,000 joules over those 5 seconds to looking at what this event would release. So that volume of rock, that 455 million cubic meters of rock, would release something like, we're going to jump from humans here now to atomic bombs, because we have to understand the scale.
Wow.
So the little boy bomb dropped on Hiroshima as part of near the end of World War II released 65 terajoules, so 6.5 times 10 to the 12 joules of energy.
Too many numbers for me.
Hafthor Bjornsson released 5,000 joules, 5 times 10 to the third. So this is, I mean, it's a billion times, essentially, a billion times as much energy. Okay, so Hafthor is pretty strong, but you can't compete with Hiroshima. Mm-hmm. Okay, so Hiroshima, 67 terajoules. Working out the back of the envelope, energy released during this slide, just moving that much mass into the ocean, dropping on average a half a kilometer, right? Because it extends a full kilometer in elevation, so the average is half. Dropping that mass half a kilometer vertically releases equivalent of energy of 90 little boy Hiroshima explosions.
Oh my God.
90 atomic bombs. That's how much energy is stored just in the gravitational attraction of the materials on the mountainside.
Wow.
So rock, water, we all know that how much water weighs. What is it? 8 pounds per gallon, a kilogram per liter. So that's 1,000 kilograms per cubic meter.
Wow.
Ice is 900 kilograms or so, which is why ice floats on water. Rock's about 2,600 kilograms per cubic meter. And so the amount of energy in any of these systems, glaciers, as I mentioned, grow generally at higher elevations in the mountains, because that's where it's cold, that's where the snow falls. Yep. So glaciers represent, and the reason they represent a hazard is they represent an energy supply. They represent potential energy. And so ice, rock, water, all of those things placed up high in a precarious position, that is all energy available to do damage as it transitions from potential energy sitting there to kinetic energy moving, accelerating downhill. Wow. You can use that energy to melt water. So you move from ice, solid ice, to liquid water. That water can mobilize more sediment. And so this is one example of a rock fall hitting water. But glacier hazards are often mixtures of water, ice, and rock, or glacier source water and rock. And so these mixtures can become really dangerous. And the biggest events, like this one, the hazard here isn't the rock fall, right? Mm-hmm. The hazard here is the wave, is the currents. Yep. And so what these glacier hazards often represent are hazard cascades, where it starts as one thing and then progresses through a chain of events into other hazards. So the largest glacier hazards often are these hazard chains. Wow. And this is probably the biggest example that is currently threatening anybody, probably on Earth, in terms of glacial hazards. The biggest in terms of energy release. I don't mean in terms of potential loss of life.
In terms of the number of people exposed and whatnot. This is such great, like, what a great way to conceptualize and think about it, because this is like the mixing of our two fields.
To go back to Hafthor just for a moment. So his lift, that the barbells, that equates to about a cube of rock, 60 centimeters on a side. So that big.
Wow.
So that's what he lifted at the average density of rock. And so now imagine, instead of this volume, which is the limit of any human has ever lifted in a deadlift, go from point 0.2 cubic meters is what this means. 0.6 times 0.6 times 0.6, that's 0.2 cubic meters to 455 million cubic meters. It's unimaginable how much energy is available.
Yeah.
And it's so things can't happen without the energy to do so. And so this is how I like to approach these and understand them for my pea brain, because
Yeah.
these scales are beyond anything that we can really visualize without figuring out, okay, how can I visualize this in a way that makes sense to me. So that's how large these hazards are.
That's brilliant. That's what a great way to think about it. So, I mean, staying on the topic of hazards,
Yeah.
there are so many different glacier hazards, and as I'm reading about glaciers, I'm going, oh my God, there's like there's so many of them. So
Yeah.
I guess let's just ask the question, and you can take it any way you'd like. Like, what are the other glacier hazards that can be produced from melting glaciers?
Yeah, so as I mentioned, glaciers are fantastic at carving away the landscape and carving away these deepened bowls and then moving sediments down. They carry sediments, they bulldoze them around. And so the hazards really emerge when they start to retreat, because thin and retreat. So we always talk about the retreat of a glacier. What's significant is the loss of volume of ice. And so if they've carved this, how can I do this with my arms here yet again? If they've carved this over deepened basin here. So over deepened means it's deeper up valley and gets shallower down valley. And so then further off my elbow is further down valley. So glaciers carve these deep bowls and excavate sediments, and et cetera. And so if the glacier's here, it's occupying that bowl. There's no space for water to really accumulate, not a full volume of water. There's water beneath the ice, so glaciers can release floods from subglacial waters, but those are typically smaller in volume and not a concern. When the glacier thins and retreats, as it thins, the intersection with land goes back down that adverse slope. And so this is now space available for water to fill.
Wow.
And the more retreat you have, the more volume it leaves behind. And so now here, this needn't be a bedrock rise. Sometimes it is, but if this rise here that my elbow is representing is instead sediments that have bulldozed into place, then you have a weak dam that holds back a significant volume of water, potentially a few square kilometers and maybe a couple 100 meters depth. So that's cubic kilometers of water held behind this earthen dam. And so these are if that dam is breached, and the breach can occur after heavy rainstorms, if you fill that lake basin up and then it overtops that dam, or if you have a heat wave and you have excessive volumes of meltwater, you can fill that up to overtopping. Or if you have some sort of landslide that tumbles into that lake, wave action can overtop the dam. So once you overtop that dam and it's unconsolidated sediments, they just erode away, and the more that flows, the faster, the greater the volume, the more and more it erodes away. So that's a positive feedback, like we mentioned. Once flow starts, it erodes. Once the erosion happens, the flow accelerates. Once the flow accelerates, the erosion accelerates. Once the erosion accelerates, the flow accelerates. So it's this positive feedback loop that really rapidly just destroys the dam and releases up to several cubic kilometers of water.
Yeah, the big flood.
Yep.
Wow.
And so these are probably the number one hazard in terms of threat to life, human life, in terms of numbers of events. It's really, these are of huge concern in a number of parts of the world. So right now
we call these Glacier Lake floods, or what's the
there's a great term, Glacial Lake Outburst Floods, GLOFs.
GLOFs. Thank you.
Yeah, GLOF. It's easier to say. I'm not hugely fond of it, but let's go with it. So GLOFs, or Glacial Lake Outburst Floods. So that's one type. So you can breach a moraine dam.
Right.
The other type of GLOF is when a glacier, let's say one glacier flows into another. So much like a creek enters a river, or a minor river enters a major one, the Missouri entering the Mississippi, glaciers can also merge from a network of mountain valleys.
Right.
So if glaciers thin, or if one of the glaciers that once reached the main glacier trunk, retreats, it also leaves space for a lake to accumulate. And then you have ice damming a lake. And an ice dam lake is inherently unstable because ice floats.
Yeah.
And so as soon as the lake gets high enough to start, it doesn't even need to float the glacier. It can just start pushing water into the subglacial drainage system. Once that occurs, the same sort of feedback occurs because you have water flowing beneath the ice, and as it flows, it erodes the ice away, creating a bigger channel, which allows the flow to accelerate, which generates more melt, opens up the channel more. So it's another feedback, positive feedback that can cause a runaway. So these are also found. They're less common. They're less the places I know they're occurring. So right now, Juneau, Alaska has one that's happened every year since 2011. 2011 was the first year it had ever happened. Because of a little side basin called Suicide Basin, where a glacier that used to cascade down from a higher plateau into this little side basin in the Mendenhall Glacier retreated, and so it no longer cascaded in, and it, without adding ice from this this glacier from above, the ice level in that basin dropped down. Oh, it's not even really gonna. Oh, there you go. This is the
And
red
so-
zone by, can you see the red zone by Juneau? It's almost in the very center of the map.
Yeah. So just in the south of Alaska where it's red. And so the red parts of this map, and for people who are audio
Yeah.
only, we're showing a map that has a number of areas where the GLOFs are a higher risk to occur, either because of exposure to population or because of the severity of the event, if I'm correct in this one. And so in Juneau, which is South Alaska, we see red, which is higher risk. And then when we get to Alberta, which we'll talk about in a few minutes, we also see some red. Please finish your point.
Yeah, so Suicide Bay, I happened to be on a glacier above Juneau when the first outburst occurred, which is just serendipity. So I got off the glacier to news of this outburst flood. So essentially what happened is that with Suicide Glacier no longer contributing ice to that little basin, and it's not even a square kilometer on the side of the Mendenhall, instead of ice flowing out of that basin into the Mendenhall Glacier, ice is now kind of backing into that basin from Mendenhall. Not as effectively, and it's filling, the rest of the space is filling with water. And then once it gets high enough, it escapes, sneaks beneath the Mendenhall, out the terminus, through Mendenhall River, through the town of Juneau, because Juneau, I believe, is the only North American town site with a glacier within its borough limits. It's a remarkable place. And it's the only glacier, I'll also say, the only glacier in North America visited by more tourists every year than our own Athabasca Glacier in the Rockies.
Wow.
So it's a pretty heavily touristy area. Fortunately, none of the outburst floods, and they've occurred either every year since 2011 or every year but one. I forget. There might be one year where it didn't happen to develop, but there's been no loss of life. There's been some property damage, some inundation of homes, some erosion of the riverbanks, but flooding of trails and roads. And they tend to monitor it, as you might imagine, pretty closely and shut down the roads and have people evacuate as necessary. So this is not one of the more dangerous events, which is pretty lucky because this is the state capital of Alaska. And it's isolated. You can only get to Juneau via boat or plane. There's no roadway that gets you to Juneau. So serious evacuations would be quite difficult there, where this is a different sort of hazard.
Yeah, absolutely. So, and I recognize in 2023, you were part of a group of scholars who did Himalayan risk was it with GLOFs or was it with landslides?
That's a great question. The earliest news reports reported this event, which happened in the Chamoli district. So I was involved with some work on an event that happened in February of 2021. And this is in the Chamoli district of India, an area that's been hit in the past very heavily by GLOFs, by Glacial Lake Outburst Floods. And so the initial thought was that this event was also a Glacial Lake Outburst Flood. And what analysis showed was that isn't the case, that instead, what happened in this event was a rock and ice fall from a nearby peak. And so the Himalaya are, I've not been there. I've been in some pretty big mountains in Yukon and Alaska, but I have not seen mountains of the scale of the Himalaya or the Karakoram or the Hindu Kush. I've just not, I can't picture that
Vast.
greater still scale in my mind. And so the numbers here are hard for me to imagine because they are the distances of fall, for example, are so extreme. So what happened is that on this day, February 7th, at about 10:21 a.m., 25 million cubic meters of rock and ice fell. And it fell from a peak, a vertical distance before it hit the valley floor of 1,800 meters, so nearly 2 kilometers of vertical fall, down about a 45-degree slope. And so that was about 80% rock and 20% water. And looking again at the potential energy release and that much of a fall. And then once it hit the valley floor, it continued and flowed down several kilometers down a river network of rivers.
Mm-hmm.
Another 1,800 meters of vertical elevation, 1,600 meters of vertical elevation lost before hitting the first hydropower installation.
Wow.
So it destroyed that, kept going, kept dropping in elevation. And again, dropping in elevation is nothing more than gaining of energy. And then it hit a second power plant. And then eventually over the course of weeks, reached the Ganges and then out to the Indian Ocean. So it was an event that killed over 200 people.
Mm-hmm.
Destroyed a lot of infrastructure. An event that, is quite destructive and a lot of loss of life. And so the reason this one unfolded is because of the energy available. It unfolded the way it did because of the energy available was extreme. That first fall, to go back to Hiroshima's, was something like 15 Hiroshimas of energy release. And that was enough energy overall through this, and another 14 before it hit that first power plant. So that's enough energy to convert all of the ice into water, which is remarkably difficult to do. It takes a lot of energy to melt ice. But because it was so much rock with a bit of ice, that additional potential energy of the more dense rock was enough to melt the ice. And so you ended up with rough, again, 25 million cubic meters of slush. And so these mixtures of water and rock are called debris flows. And they're immensely damaging. So it was the worst case scenario in many ways. First off, because these great fall distances, the great loss of elevation, was there enough energy to melt all of the ice into water? And only because it was 80% rock was there enough potential energy, even given that fall length, to convert all the ice.
Wow.
And so, and that mixture, 80% rock, 20% water, is the most destructive mix that you can have. It's fluid. It's strangely fluid. It flows very readily. It flows very quickly because it is very dense. It's about 2.3 times the density of water. It's almost the density of rock because it's, again, mainly rock. And so worst case scenario, right? Huge volume, enough energy to melt the ice to create this most damaging debris flow, 80% rock and sediment, 20% water. And so again, it carried all the way to the Indian Ocean over the course of weeks. It wrecked water supply, water quality, 1,000 kilometers away. Remarkable amount of damage.
Wow.
And so it was an interesting event because I learned about it. I became involved on social media because somebody asked about the water, where the water came from, and could you melt that much ice? And so I started to do back of the envelope calculations, and I realized that it's really hard to melt that much ice, and only because there was that much rock and that much of a fall distance did this disaster work out the way it did.
Wow.
So it was a worst case, and so it's a real tragedy when you see so many worst case scenarios happening in real time, as we are these days.
Yeah.
Fire, flood, rockfall, GLOFs, you name it, they're happening because of the changes we're experiencing.
Wow. So let's just quickly go to this photo, which is a similar map to the Alaskan map of GLOFs.
Yeah.
So these GLOFs are, you were talking about, so this map, for the audio viewers, it's showing the the high risks of GLOFs around the central, the south, the eastern, the western Himalayas, which
Yeah,
are that India-China border, if you know where Tibet is, right
yeah,
there. And then and uh, I think it was about 2 months ago, early August, we actually saw in Uttarkashi, which I think is the district you're talking about, or the province. There was a similar cloud burst which dropped a astronomical amount of rain from that high to low, causing a lot of these grand, very large floods. So
yeah.
this picture showing a lot of high risk from GLOFs.
Yeah, it's remarkable. I mean, that entire sea of red there in the high Asian mountains, the HKH, the Hindu Kush, the
Mhm.
Karakoram, and the Himalaya, plus the Tian Shan. It's an amazingly densely populated area for the
Very.
topography there.
Mhm.
Um, it's this is the region with the greatest hazard to human life, risk to human life of these GLOFs. Pakistan is probably the individual country with the greatest increasing risk. A recent study showed that of the 7,000 or so glaciers they looked at via satellite images, something like 3,000 of them now have recently formed glacier lakes. 3,044 new glacier lakes have formed between 2001 and 2013 in Pakistan.
Wow.
So this risk is growing. It's a temporary one as long as there's glaciers receding. They're a risk. So it's temporary in the grand scheme of things, but
Mhm.
it's probably our foreseeable future as well. And so to go a little bit broader than just this map, because Peru is also an area of high risk. Something like 15 million people overall are exposed to potential impacts from these glacial lake outburst floods. And that's a number that's kind of hard to wrap your brain around. And that number, I to put it into context, so that 15 million people, they all of those live within 50 kilometers of a glacier lake, so downstream of a glacier lake, and
Mhm.
within 1 kilometer of a likely uh, glacial lake outburst flood runout track. So
Wow.
1 kilometer with these levels of energy is not comfortable. I'm going to say it's not as if that kilometer is like you're a kilometer away from seashore when there's a tsunami, assuming some topography. It is the energetics here are enough that these floods are so these debris flows are so fluid and mobile
Hmm.
that they can really go far. One of the things we observed in that event that I mentioned in the Chamali district of 2021 was that satellite image analysis showed that there were 13-meter long boulders placed about 200 meters up on ridge lines where the flow was able to just shoot right over the ridge lines, leaving these 13-meter long boulders behind. So the
Wow.
energetics here, again, they're really hard to fathom. They're hard to imagine the power, the speed, the destructiveness. One of the interesting things about this Chamali event was just the absolute breadth and wealth of information available from. So the initial work was included things like an analysis of seismic signals to determine the moment the event started and even how long it took to do that initial fall. It took about 60 seconds to fall that initial distance.
Wow.
And so that's the first estimate of velocities, right? Other velocity estimates come from social media because people have their phones out and are
Mhm.
recording these things destroying the power plants. And sure, they're jumpy videos because people are also simultaneously running for their lives.
Yep.
But analysis of those videos showed things like when it first hit that first power plant, it was moving 25 meters per second. And so imagining a flow that dense moving at that speed, if you're in the way, there's no getting out of the way, right? So
Wow.
social media, the seismic observation networks, the wealth of satellite observations we have today is remarkable. And so moving forward, looking at how to mitigate these hazards, if you have people turning off their cell phones or other notification systems, it's tough.
Yeah.
But even the foundational work of monitoring these changes, monitoring spots that might fail. This analysis afterward of previously taken older satellite images shows that there was a failure line, a crack in the ice above the zone that failed. And so
Wow.
that had been that precursor indicator had been there for several years. And it's not like it's anybody's fault that it wasn't noticed, because this area is so vast. There are thousands of glaciers, and every one has crevasses on it. And
Yeah.
so looking at small changes is difficult. And so I'm hoping that things like this would be one potentially phenomenal, life-saving application of AI, is to analyze images as they come in without the burden of having to eat or sleep or take
Mhm.
washroom breaks.
Mhm.
If computers can be trained to recognize threatening changes such as these hazardous changes, then that would be a phenomenal use of AI. I think most of our common day uses today are a bit misguided. Mainly artificial intelligence, the main goal of it today is increasing the throughput of clicks on advertising on websites. So let's
Mhm.
retask it, shall we, to save lives rather than boost bottom lines. That seems like a no-brainer to me.
And it's kind of contributing to the overall risk of glacier melt
Oh,
itself.
isn't that ironic? Yeah,
But too, right? So, yeah.
yeah. So that
So,
was an interesting event, and things like the social media wrinkle, learning about it, learning about the velocities from social media, learning about when it hit other areas from social media, looking
mhm.
at the satellite imagery, looking at all the there were scientists from North America, South America, Europe, Asia, all contributing to this study. It was a remarkable study. And I will shout out to my colleague Dan Sugar down at University of Calgary. He was the
Okay.
one that organized this big group, and ushered this, I won't say tome of a work, because we had to streamline it down to a tiny format. But to do that with so many scientists was just a remarkable feat and really rewarding. So I was really happy to be involved with that.
Yeah, and he's an absolute expert. He's the expert. His
Oh yeah,
expertise lies in landslides, and he
yep,
did some work on the recent, I think, June or July landslide that happened in Western Canada, in near the Banff
yep,
National Park and whatnot. So, yeah,
yep.
brilliant.
Yeah, I'm very that spot's one I'm very familiar with. I've done some work up on the Bow Glacier, right above it, and so yeah, that was a really tragic event. So it was a rock fall,
Hmm.
for the audience. It was a rock fall that killed 2 people and
Hmm.
threatened several others, because the rock fall is adjacent to this beautiful waterfall that cascades down from a lake called Iceberg Lake. Another of these little basins formed by when the Bow Glacier was more extensive. It had carved this bowl out, cascaded down it to the bowl into the basin that people view the waterfall from.
Wow.
And in past times, extended past that to carve out what's now Bow Lake, right
Hmm.
up the Icefield Parkway. So again, these glaciers are really good at carving these landscapes that are U-shaped and undulating in long valley profile. So leaving all these hazards, but also alpine lakes behind. So one could argue that the retreat of the Bow since the Little Ice Age, maximal extent of roughly 1880, that revealed that rock face that
Huh.
killed 2 people this summer.
Isn't
Um,
that something?
yeah,
So,
so that's another example of deep buttressing, I would say,
huh. So
but on a
what
much
when
smaller scale.
and I guess if I could just like the broad overview of the risks that we've already talked about. Number
Yeah,
one, the rock slides and landslides from this debuttressing event, and um,
yeah,
just the way that you explain that makes so much sense to me, because the Earth is constantly shifting, and
yep,
eventually some things are going to overshift. So landslides from debuttressing. We have our GLOFs, our Glacier Lake Outburst Floods.
yeah,
Um, and then we also have, the debris flow that I think is really interesting, that mixture of rock and ice. And
yeah.
that overall, I mean, that is really intense. Is there any other like major hazards that glacier melt can really lead to or cause?
Yeah, so I think the major hazards are these, and most of them, aside from that Barry Arm example that just goes right into the fjord, most of them are these hazard cascades that start as something, but because glaciers are perched high, they've by glacier activity. They've left a lot of loose rock on the landscape. They are themselves water. So if you liberate that water, if the water is contained within an upper basin, say between the terminal moraine, the debris bulldozed by the glacier at its maximum recent extent, and then as the glacier retreats, again, it leaves behind a lake. So there's water and sediment right there, poised and ready to go by some trigger, right? The trigger could be, like I mentioned, rainfall, extreme melt, landslide. Or if you have ice perched up high enough and it falls, especially if it falls with rock, then that can also generate melt that mixes with the fractured rock to give you another debris flow. So debris flows are probably, and these are both hazard cascades, right? It was a dammed lake release that liberates water and rock from high elevation, or falling ice and rock that morphs into a mixture of ice and water through losing elevation. So these materials perched high in mountains can generate debris flows that go a long way. And so that's probably the greatest overall hazard. However you end up with that mixture. You can also get that mixture by looking at Mount Rainier and looking at its recent history. So the last 10,000 years, a number of events where volcanic activity melted the glaciers that sit on it.
Yep.
Boom. They call those lahars, or mud flows.
Yeah.
And those, if you look at the geologic record around Puget Sound, I wouldn't be all that comfortable if I'm one of the 4.5 million people living there right now, because those lahars, they run, I think I have a cheat sheet here for that as well. Let's see. Yeah, so they can go 70 or 80 kilometers an hour through the valleyways they take. So if you're along the Puyallup River, for example, that's a prime lahar pathway. And there have been flows that go 80 or 70 or 80 kilometers an hour. And they know that from how far that they slosh up the sides, right? They reach Puget Sound. They reach Tacoma, 50 kilometers away from the mountain.
Yeah. Hey.
In the valleys, they can be 150 meters deep when they're confined. They spread out because they're fluid. They spread out when it reach the end of the valley. And so again, another way to get this mixture of rock and water that's a very fluid, mobile flow, very dense fluid mobile flow. And when they stop, they set up like concrete. So it's just all sorts of mess, all sorts of damage, and all sorts of hazard. All of it from materials perched up high, waiting to form a debris flow through these various hazard cascades. So I think that is the greatest hazard. Yeah.
Wow. That and you know, all of this isn't even accounting for like one of our big global shifts, climate change, and how human-induced climate change is influencing a lot of just the natural patterns around. And I guess that's really a nice segue. How, like, broad strokes overall for you, how is climate change really affecting glaciers and glacier melt?
Yeah, it's not a pretty picture. I mean, something like 95% or more of glaciers worldwide are thinning and retreating. They're losing volume. There's a few that are doing well, or seem to be doing well. There's some that are apparently doing well because they're advancing from various dynamical processes. So some glaciers will surge and then on a cycle that's independent from climate, or tidewater glaciers have this advance and retreat cycle that's independent of climate, largely independent anyway. But and even some glaciers, in the lucky glaciers in the right spot where a warming climate means more evaporation from the oceans and more rain, more snowfall where they happen to be sitting, that some glaciers are benefiting. So, but 95% are losing mass. And so there's a couple of ways to express that mass loss. One is the way that the World Glacier Monitoring Service, which is an international group, puts it, is that they look at a number of indicator glaciers, so glaciers that have been studied for more than 30 years, every year, with extensive measurements annually to understand how they're responding. There's about 60 of those. They're called reference glaciers. They're losing the reference glaciers, and so they're adding new benchmark glaciers that are well studied but have less than 30 years of record. So this is where we're at. We're losing our indicator glaciers, our reference glaciers, and we have to incorporate new ones. So if you take those glaciers as representative of the areas in which they sit, and they're very careful when they select these to do so, that these indicator glaciers suggest that worldwide glaciers have lost since 1960 over their entire area, average over their entire areas of glaciers, 25 meters of thickness.
Oh.
It's a lot. It's a lot of volume. All the area times 25 meters is a huge volume. Stated differently, so a recent study, actually a study from February of this year, says that between 2000 and 2023, so the 24-year span, glaciers worldwide lost on average annually 273 gigatons of ice. And so gigaton is hard to imagine.
Wow.
But it works out. If you melt a gigaton of ice, you get a gigaton of water. It makes sense. And a gigaton of water is a cubic kilometer, a kilometer tall, a kilometer wide, a kilometer deep. So worldwide, glaciers are losing 273 cubic kilometers worth of water annually in modern times. And that's the number averaged between 2000 and 2023.
Yeah.
Modern loss is greater than that. So that's a 24-year average. The last 10 years is more rapid.
Wow.
It was less rapid in the earliest part of this record. So that's 5% of all glacier volumes across the world being lost in that 24-year period, not including Antarctica and Greenland. So it's mountain glaciers and ice fields and ice caps. Yeah. Just 5% in that time, which has effects, because glaciers have a role to play in water resources, in ecosystems, in the world that we know, right? So if you're a trout fisherman you like to go to the foothills of the Rockies and fish for bull trout and cutthroat trout, those trout rely on the cold waters supplied by the glaciers. If you're growing crops in Alberta, a portion of the water that reaches you in summer in particular, where glaciers are contributing most to rivers. So rainfall is at its minimum. Snow melts at its minimum. And so what really picks up the slack in late summer is glaciers, this storage, this reservoir of water in solid form. And so it takes all summer, part of the summer to melt the snow off and to reveal the ice. And once the ice is revealed, then it can melt more readily. And so late summer, you get this pulse of water from glaciers. Wow. And so we have come to rely on that pulse of water to supply, our populations, our agriculture, our industry, the ecosystems that we all rely on. And so what we expect to see is, over the next several decades, we're going to reach peak water, as they call it. And that's a term not all hydrologists like or glaciologists like, but what it means is that between now and about 2040, we expect that the contribution of glacier melt and glacier mass loss to our rivers will peak. And following that, their ability to supply late summer water will decline, because there won't be enough ice present to keep that additional flow going. So there's some changes coming, and we're going to have to adjust to them, whether we like it or not, because the additional supply we've been relying on will be exhausted.
And isn't it just so fascinating? On one side you have the intensity of some of these hazards increasing just due to sometimes the sheer coincidence of proximity and geography and whatnot, the amount of people. But then also on the other side, you have the almost overall reduction of an entire ecosystem that is slowly diminishing. What a wow, hey?
Yeah, I don't want to oversell the hazard here. I mean, it's a significant one, right? Mm-hmm. But the good news, if there is some, and I always like to end on good news. I teach my class in general Earth system science is always a depressing one, because we end on climate change. Yeah. But if there's good news, it's that where a glacier sits today is a spot that receives more precipitation than everywhere around it, right? It grew there for a reason.
Yeah.
And so, we're going to lose a bit. We're going to lose the portion of the river flow that is wastage of that ice reservoir, right? Mm-hmm. The amount of volume not being replaced annually. But still, most of the flow, most of the meltwater from a glacier is replaced annually. Still, it's a fraction of the glacier that's lost every year. Yeah. So it's that loss, it's the amount that's being lost annually that we're going to lose. We're going to lose the timing of it. We're going to lose that late summer pulse when it's no longer glacier. But that landscape's going to receive probably similar rainfall. In some locations more, because oceans are warming, the atmosphere is warming. That means more evaporation. Warmer atmosphere can carry more water vapor in it. So that means more precipitation. So there's a balance here. And again, some glaciers are currently healthy from that balance, but most aren't. So there are some, we can expect hopefully not much overall decrease in water volume. We just it'll be more peaky. It'll be more flood prone. It'll be less predictable that way. And we won't have that late summer pulse. So I don't know if that means people are going to respond by storing water, by additional dams on rivers, which are also problematic, of course. They fill, they change the discharge, it changes the whole ecosystem downstream. So there's no easy answers here, but I hope it's not all dire, only slightly dire.
I do have one more question. So one of the things that has really got me interested is you talked about the Bow River and a few other rivers throughout Alberta. Yep. Do glaciers feed our drinking water? And that process of, the building on the ice pack and whatnot, and already what you've described over the next 14 years, our glaciers might see hopefully a little more rainfall. Do you expect like the rivers of Alberta to really recede and then have to get wider and then recede, or how does that look?
Yeah, so first off, Alberta has a lot of glacier-fed rivers. Most of the main rivers in Alberta are glacier-fed. So the Peace, the Wapiti, the Smoky, Little Smoky, Athabasca, Pembina, Brazeau, North Saskatchewan, Red Deer, Elbow, and Bow rivers. They're all glacier-fed. And a lot of streams that we can't name that contribute to these rivers. So it's probably easier to list the major rivers that aren't, right? There's the Hay. There's the Hay and another one in the north that are fed by muskeg. There's
the Athabasca? Or no, the Peace?
Peace is glacier fed. It's another one that starts with a C8. I forget what it is. But Old Man comes not from glaciers, but the Alpine anyway. The Milk River doesn't originate at a glacier, but these other ones are glacier fed. They originate, the upper headwaters is a glacier sitting on the landscape.
Wow.
Of those, the best studied in terms of glacier contributions to the flow is the Bow. And there's a study in 2014 by Bash and Marshall that I really like. It's hard to tell from the study what is glacier contribution from sustainable melt that is replaced every winter versus wastage or loss. So I don't know how much is sustainable, how much isn't, but it's instructive anyway to see how much of the water flowing through Calgary, and this is what this study is looking at, how much water flowing through Calgary comes from glaciers, the Bow and other glaciers. And so the number is going to seem small. Annually, about 3% of the discharge is from glaciers, directly from glaciers. And the reason it's so small is that there's a vast area of land that feeds Calgary, even though Calgary is that as close as it is to the mountains. Mm-hmm. And so all of the landscape contributes via melting of snow, via infiltration of rainwater into the groundwater system, and the groundwater system, very slow flow through sediments, does contribute what they call base flow to rivers. So in the wintertime, when it's frozen, when the North Saskatchewan is frozen through Edmonton, that's mainly base flow. It's water coming in from the groundwater system into the river basin. So 3% annually is from glacier, directly from glacier melt. In summer, the numbers come up. It's about 4 to 6% of overall summer. So summer, again, this is when glaciers peak. In August, it can be 8 to 20% of the Bow River's flow comes from glaciers. So that 20%, if you were to remove 20% on the hottest days, that would be noticeable, because that's when agriculture needs water the most. That's when all of us tend to, for good or for ill, water lawns, right? It's when we go to the water park. We use water in summer. And so if 3% doesn't sound like, we can deal with 3% loss annually. 20%. Yeah, but 20% in August, even 8%, low number there for the August range, again, 8 to 20%. That's a big change.
Wow.
And so in Edmonton, we're much further from the mountains. And so the contribution from glaciers is much smaller. Mm-hmm. But I still think that thinking of it, even as small as being negligible or unimportant, is probably not the way to think about it. If you look at the Colorado River, it doesn't reach, what is that, the Gulf of California anymore, right? In summer, because it is so overdrawn that it goes dry before reaching the destination. Mm-hmm. And so 3% more to that river would be huge, right? People would celebrate a 3% bump in the river flow there. So when we've all heard for decades people saying the next wars will be fought over water, not oil. 3%, it's not nothing.
Yeah, that's substantial. Yeah, and especially as we consider the overall impacts and influences from how the sporadicness of water and rainfall and how those those patterns are changing too. So that is just so interesting, right? And I love the way that you really frame that well. It's we can talk about like the averages, and the average might look like, oh, it's just 3%, but in August it's 20, and it's going to be, that's astronomical. Whereas in January, we're not thinking about that. We don't need to necessarily think about that as much.
Yeah. Well, it's interesting. And so let me just clarify that study looked at river flow from 2000, 2009. So it's, again, all of these are moving targets. Things are changing in real time. Not always for the good, but a place that really does rely on river water for more reasons, and another use of glacier waters worldwide is for hydropower generation. And so, for example, Yukon generates more than 90% of its power by hydro. Mainly, the main generator is in Whitehorse on the Yukon River. So I was involved with a couple of studies a number of years ago now, looking at the fate of water in Yukon and how changes in glacier melt and glacier wastage are going to impact Yukon's ability to generate hydropower, especially at the shoulders of the viable season. So they have no problem generating abundant power hydroelectrically in summer, right? It's in winter when the demand is highest and the river flows are, again, reduced to that base flow, that they can't supply all the energy they need. So they have to buy, currently they're switching from diesel generators to sustainable supplies. So that's great news, but they still have to buy diesel for the shoulder seasons and winter. And so knowing the duration of shoulder seasons does define how much fuel they need to buy.
Wow.
And if you buy too much, diesel doesn't last. No. If you buy too little, you have to truck it up, right? In winter to Yukon. It's not a cheap, neither is a cheap proposition. And so there, the river flow, we looked at the contributions of glaciers to the upper Yukon, and there we found a higher contribution. So 23%, fully 23% of modern flow of the Yukon River at Whitehorse is from glaciers.
Wow.
And so of that, and this is, I love this study because it allowed us to break this down. And this is modeling work done. I'm going to give a shout out to Yost Samuels. He was a postdoc under me. Chris DeBeer before him. Great researchers, great people to work with. So of the 23% that the upper Yukon River receives from glaciers, 7% was from permanent loss of ice, and 16% of, again, adding to 23, was from melt. So replaceable, replenishable supply from new snowfall each winter. So yeah, it's probably something like 1/3, 2/3. So these resources are finite, but and have a expiry date, if you will.
Wow. What and I mean, like, we've based a lot of our systems and our infrastructure off of like the rivers, the natural flow of things. So what a brilliant way to contextualize it. Okay, so the final question of today:
Yeah.
and I think you've done a brilliant job of this, and I think I know what you're going to say is, how do you communicate these risks in your perspective? And as somebody who
Yeah.
might be in like the field of disasters, who is looking to, mitigate and increase the risk awareness of these things, how do you just go about, I guess, not only talking about them, but conceptualizing them, just like you kind of have?
Yeah, that's a challenge. I mean, as you know, people don't like to receive Amber Alerts. They're startling. But I mean, I keep my eyes peeled for that license plate and whatever it is, silver SUV. You know, it's I like to think that society benefits from these activities, and despite the potential for annoyance. But it's the biggest challenge I think faced is that map you showed of the high Asian mountains.
We're gonna go back to it.
Not many of those are wealthy nations, right? Of those nations, I would say perhaps only China would be considered wealthy. And so, what was remarkable in the work we did on the Chamali disaster that I described was just the amount of expertise and the wealth of tools brought to bear to understand that event.
Mm.
And that expertise was not entirely Western. It wasn't entirely European. There was local expertise that were foundational contributions to that study. But they're working in a paucity of funding. They don't have the satellites in the air. They don't have the resources that Europe and the Americas do. And so many of these regions that are impacted, and this is true also of Peru, the other region that is most strongly impacted by these glacial lake outburst floods, there's not much wealth, there's not much monitoring, and monitoring comes from wealth. You need funds to monitor things. And so, and this is another disappointment of the defunding of scientific capacity in the U.S. right now, because NASA, JPL, these are the folks that operate the monitoring satellites and that are planning to launch more. So we need to rely more on the European Space Agency and other allies in that regard. So losing capacity today is disastrous, because we are otherwise in a golden age of ability, right? Of understanding, of monitoring, of tools for for forewarning. I believe it was that Boxing Day tsunami in Indonesia that finally kicked the U.S. into putting tsunami hazard signs all along coastal Americas, right? They didn't exist beforehand, and I think people want to avoid repeating mistakes, avoid allowing these events to take human lives. And so I think that it will take a concerted effort amongst the wealthier nations to support the poorer nations in moving forward. So how that is translated to the ground in areas that are directly impacted, that's a tough challenge. I mean, imagine the cellular coverage in some of these deep Himalayan valleys, right? Yeah. And the valleys the valley system that hazard cascade came down from this peak in the Himalaya. It's, again, hydropower is being built there because we are always demanding more power, and we always want the power to be carbon neutral, carbon free. So hydropower is a great use of steep terrains with heavy river flows, but it's also a very hazardous place. And the people in that valley are not wealthy people. They're traditional peoples who have been battling with development. So forestry in the 70s came in to remove their forests that they relied on for fuel and heating. These hydropower installations were built with maybe not the most stringent ecological analyses. So
you could say it.
Don't worry. Same issues we're facing here. Think of the site. What is it? Site C dam in BC. The same issues of use of land and autonomy and respect for those that are existing there are are brought to bear. So it's a huge challenge. I mean, Alaska is, Whittier. Yeah, when Barry Arm goes, you're going to want to get uphill, but they're going to have the warning system.
Mm-hmm.
If you're on a cruise ship, you're probably monitoring every day the USGS site on the Barry Arm landslide to see whether today is a good day or bad day to go out, to roll the dice on today. Many people don't have that opportunity, and I don't know, frankly, how we can reliably provide more safety for those people. It's a tough challenge.
Yeah. Early warnings are what
Yeah.
save lives, right? It's
Exactly.
the ability to give somebody the information so that they can get themselves out or make the
Yep.
best decision for themselves, right?
Yep.
Yeah. A very
Yeah. So
that that's one of the fundamental things that we hear with every sort of disaster. And after
Yep.
going back to the Indonesia 2004 Boxing Day tsunami, early warnings were the primary determinant of how okay some places were versus just areas that got hit because they didn't know what was happening. So,
yeah.
well said.
Yeah, I was a postdoc at Berkeley at the time,
Hmm.
and a colleague of mine had a beeper. He helped maintain um, the seismic network that UC Berkeley operated,
Oh,
and he got a page on his beeper that there had been an earthquake. So he knew in Berkeley, but the folks in Indonesia didn't know.
wow.
So that's again, if you think of safety management,
Yeah.
that's an absolute failure of a safety plan.
Yeah,
right.
absolutely.
There was those that knew didn't communicate, and I'm not blaming him for that.
Mm-hmm.
My colleague for that. But it seems like in hindsight, as it always does, it seems like an obvious gap.
Yeah.
And so we have satellites that can look for, widening crevasses on perched blocks of ice, perched glaciers. We have seismic monitoring that can detect events in real time, so long as, again, they're monitored. It's not automatic. There's a lot of work done to tease out the seismic signals, details of this disaster. But the building blocks are there for more capability. It's translating that again from the scientists and the agencies that have the tools and can build the monitoring systems. Communicating those in real time to the people is always going to be the challenge in these areas. Is going to be the main challenge in these areas. So I would love to find a way, and I know there's more monitoring in this area, in this particular area, but it's just hard to imagine. And where can you get to if you're in one of those valleys? Because if you've seen any of the footage of that event, these rock walls are sheer. They're 60, 70 degrees.
It's the straight drop, right? And especially even with the debris flow that you mentioned, I mean, like there was a video that came out just from August again, and like houses, well-constructed houses, will not even withstand anything like that. It's
the concrete hydropower stations just folded.
Yeah, exactly. And those are pure concrete in some places. So it's more so the proximity to how close you are to that area. So that's well said, right?
Yeah.
Well, perfect. So thank you again. That is all the questions I got. I just wanted to leave it to you. Do you have any final thoughts? And where can people message you or reach you if they want to connect and ask a question?
Yeah, final thoughts, boy. Glaciers are hazardous things. They
Incredible.
even to glaciologists. I unfortunately lost a colleague a couple of years ago, Maya Batia, who was studying a glacier in the Arctic, lost her life on one. It's been a number of other colleagues during my career that I've lost to on glaciers. So travel safely, please, in mountain environments. But in terms of, they're spectacular areas, and it's hard not to want to see these places and understand how they operate. And glaciers are one small aspect of these remarkable regions here on Earth, and as always, it's kind of the luck of the draw. If you're in the wrong place at the wrong time, sometimes there's not much avoiding these things. But the same can be true, crossing the street, driving to work, so cycling to work. So you have to live your life balancing the hazards and getting the most out of it. And so I think that it's a reasonable risk to take to visit these places. Again, especially with people who understand glacier travel, if you're getting on the glaciers, or the environments, the hazard you might face. So generally, if you're hiking the mountains, the most hazardous things you'll face will be water crossings and steep drop-offs, and with animals being up there as well. But so care in the mountains is always warranted. And but do go there. They're amazing places, and I find them to be refreshing for my soul, and so they're required places to visit for me, despite whatever hazards might be lurking there.
Perfect. Well, thank you again, and I just wanted to take a moment to thank you for how you reference things, how you went about providing the audience with really digestible information too. It wasn't just we can think about the little boy Hiroshima bomb, and that's what it would look like. Whereas it's a little bit more in depth. So thank you for that. You're a true expert in how you disseminate these kinds of things, and I greatly appreciate you taking the time to do this. So with that, thank you, and we'll see you next time.